chlorophyll molecules and kick off an electron to a primary acceptor, which we'll see a little bit later, and generate a highly oxidizing site down here that is oxidizing enough to oxidize water to oxygen. As you know, that is a very difficult reaction. It requires a very positive redox potential of 0.82 volts. And so we have to have a photosystem that generates this incredibly oxidizing center to oxidize oxygen. The electrons that are kicked up here then go through an electron transfer pathway similar to what we see in the mitochondria, and they pump protons, just like we found in the mitochondria. That proton gradient is used to synthesize ATP by an ATP synthase, just like we found in the mitochondria. And then the electrons are boosted up by another photosystem to a very negative redox potential, and that is negative enough to reduce NADP to NADPH. So the net result now of photosynthesis is to oxidize water to oxygen, use those electrons to reduce NADP to NADPH, so to produce reducing power, and through proton pumping to synthesize ATP. What we need to synthesize carbohydrates in the plants is reducing power, NADPH, and energy in the form of ATP. So that's what this system does. Having two photosystems is a bit like putting two batteries in series. We don't have enough energy in one photon of light to do what needs to be done here. We put two of them in series, we have enough energy to both oxidize water to oxygen and reduce NADP to NADPH. And also to have this little extra reaction here that produces ATP. So that's the overall plan of the photosynthesis. Okay, well, as you know, the primary pigments that carry this out are chlorophyll molecules. There's two types of chlorophylls, chlorophyll A and chlorophyll B, as you can see here. Chlorophyll B has an extra aldehyde right there. These side chains are kind of a long hydrocarbon type side chain, as you can see there, that gives it hydrophobicity. So these are the primary photoactive molecules, and they can be excited with light into a excited triplet state, and that is the basis of photosynthesis. Here's the spectra of these two chlorophylls, A and B here. They have an absorption out in the red region of the spectra between 650 and 670 or so, one for the B and one for the A. And then they have a bigger absorption band down here in the blue region of the spectrum. So that's what that looks like. Now, if there were only chlorophyll in the chloroplasts, this whole region here would be kind of empty. There'd be no absorption in there. And that's where a lot of the sunlight energy is located. So we have extra pigments in the plant that help out in the photosynthesis. And this is, again, from your textbook, this is kind of a combined picture of all the absorption spectra of the pigments that are present in the plants, in the chloroplasts of the plants. You can see here the red spectra is a bichloroerythrin that absorbs right in the middle here. The beta-carotene is the yellow one that you can see here. There's another one called lutein that absorbs in there. All of these pigment molecules absorb light. They are excited to a triplet state, and then they pass their energy to another molecule during a process called exciton energy transfer. And so that energy transfer process is the key to this. I just took this picture recently on a hike near the Buffalo River. It doesn't show up very well in here, but these beautiful fall colors that we get happen because when the chlorophyll goes away as the leaf dies, we then continue to see these extra pigments like the carotenes. And that's what gives us these beautiful red and yellow colors in the fall foliage. chlorophyll gives the green color. That overpowers the color that we see during the summer. But then when the leaf dies and the chlorophyll leaves, then we see these remaining pigments that are these very bright red and yellow colors. Okay, now this is a picture of that thylakoid membrane, and that's the whole chloroplast, and we're just focusing right down on that thylakoid membrane right there. And we have all of these pigments in proteins, both the extra chlorophyll molecules and the carotenoids and beta-carotene and so forth. Any one of those can absorb a photon of light. And there's thousands of these for each one of these reaction centers that finally captures the light. So any one of these can absorb that photon of light. It allows us to capture the light very, very efficiently. And then they're transferred by this energy transfer process from one pigment to another, one chlorophyll molecule to another. Maybe they start out on beta-carotene, that red guy there, then to a green chlorophyll and so forth. Finally, they get to a reaction center, and that energy of the light is trapped because that reaction center has a special chlorophyll dimer that results in a lower energy, and that is going to trap that photon of light. It cannot leave that position. We can go all over here interchangeably. Once we get there, that traps it and prepares it for the electron transfer event that leads to all of these subsequent reactions. So here then is what that looks like in another picture. All of these pigment molecules have a ground state indicated down here, and they have an excited state indicated up here. And this photon of light excites an electron from the ground state to the excited state, and then energy transfer results in the transfer of that energy, that excited state, from one pigment molecule to another. If they all have the same energy, it can go anywhere in kind of a random process. It just wanders around randomly to the different pigment chlorophyll molecules. But when it finally goes to this special pair that has a lower energy because of that special interaction, it goes to lower energy and is trapped. You can't go from lower energy to higher energy. That is forbidden by the laws of physics. But you can go from higher energy to lower energy. Once we get to that special pair in the reaction center, that excitation is trapped, and we can begin the electron transfer process. Okay, this is an overall picture of photosynthesis in plants. You have a similar picture in your textbook, but I like this one better because it shows the stoichiometry accurately here. The one in your textbook just doesn't give the stoichiometry. So I'd like to use this one here. And this is the photosystems right in here. We'll have a lot more information on those to come. But we have the photosystem 2, and that uses the energy of light to excite a special pair called P680 because it absorbs at 680 nanometers. It kicks an electron out to a pheophyton, up to a quinone called QA, over to another quinone called QB, and then it enters the soluble quinone cycle. And this has a Q cycle exactly analogous to the BC1 Q cycle in the mitochondria. And that pumps protons, and it is carried out by the cytochrome B6F complex. And that complex is completely analogous to the cytochrome BC1 complex we've already studied in the mitochondria. Meanwhile, this P680, if the electron leaves, it leaves an electron hole on P680, which is highly oxidizing. That is used by something called the oxygen evolving complex to oxidize 2 waters to 1 oxygen. And you can see the other thing it does there is that it produces 4 protons on the inside lumen of the thylakoid membrane. Meanwhile, the Q cycle, for every 4 electrons that go through the system here, 8 protons are pumped from the outside to the inside, the lumen of the thylakoid membrane. So that adds up to 12 protons. So for every 4 electrons that go through the system, we have a total of 12 protons pumped from the outside to the inside of the thylakoid. Then the electron is carried from the V6F complex by a small molecule called plastocyanin over to the photosystem 1. Plastocyanin is a copper protein. It is analogous to cytochrome C in that it shuttles the electrons through the system here. And Dr. Davis studied this in great detail in our department and found that it did obey a shuttle type of mechanism. Then the photosystem 1 uses light energy to boost these electrons up to very reducing redox potential. It reduces a small molecule called ferredoxin. That provides the electrons to a ferredoxin NADP reductase, which reduces 2 molecules of NADP to NADPH. I'm going to show the stoichiometries on the next slide here, but let me just mention them here. Each electron that is boosted in energy requires 1 photon. So let me emphasize that again. 1 photon boosts the energy of 1 electron. We have a total of 4 electrons needed to be removed from water to produce 1 oxygen. So 4 electrons go through that complete cycle to NADPH. 4 electrons are sufficient to reduce 2 NADPs to 2 NADPHs. And each of these 4 electrons requires a photon in each of the photosensors. So that photosystem requires 4 photons for the 4 electrons there, 4 more photons for the 4 electrons here. That's a total of 8 photons. So for 1 oxygen, we transfer 4 electrons to 2 NADPHs. We require 8 electrons to do that, and we pump 12 protons. That's the overall stoichiometry of the system. Then this proton gradient is used here by the ATP synthase, which is analogous to what we found in the mitochondria, to produce ATP. Notice the orientation of these membranes. The ATP synthase is pointing outwards with the lumen the inside on the bottom here. And that's useful because the outside, the stroma, is where that ATP is going to be needed. Okay? The NADPH is produced on the outside, and that's where that's going to be needed for the Kelvin cycle. So all of these guys are needed in the stroma, and so the orientation of the membrane is such that that is satisfied. So this orientation is a bit upside down compared to what we were looking at the mitochondria, but it's needed because all the reactions occur here in the stroma. So that's how that works. Here's another picture that is called the Z scheme of photosynthesis. It's the same system, but the vertical axis here represents redox potential in volts. We went through redox potentials in some detail in the mitochondrial chapter, and so this is exactly the same thing here. The 0 of the voltage scale is right there in the middle. This region up here is negative. That region down there is positive. What the photosystems do is photosystem 2, it's excited by light energy. This special pair called P680, a special pair of chlorophylls, is excited to the excited state. It kicks an electron off to the initial acceptor, which is a pheophytin A, as we'll see a little bit later. And that creates an electron hole on the P680, which is now sufficient to oxidize water to oxygen. So the excitation of the P680 creates a highly oxidizing site, which oxidizes 2 waters to 1 oxygen and 4 protons, and a highly reducing site with a potential of about -0.8 volts, which transfers electrons to pheophytin QA, QB, and then to the quinone pool in the chloroplast membrane. Notice the potentials here. Remember, the potential of the oxygen production is plus 0.82. This P680, when it is oxidized, has a potential of about plus 1.2 volts, and that's oxidizing enough to oxidize water to oxygen. We then go through the B6F complex and we pump the protons, as we've seen here. The electrons are then transferred by platinum to P700. Another photon of light comes in here, excites that up to a very reducing state. That reduces a string of compounds that I'll get into in more detail a little bit later. Finally ending up with the electron on ferredoxin. That is sufficiently reducing to reduce NADP to NADPH. Remember, this redox potential is right around minus 0.32 volts, and so that's sufficient. Again, the reason we have the two photosystems is there's not enough voltage difference in any one system to both oxidize water to oxygen and reduce the NADP to NADPH. So we need to put these two systems together in order to do that. And in addition, we get this linkage between them by cytochrome B6F that pumps protons and produces the ATP. There's also a cyclic pathway that is used under some conditions in which the ferredoxin can transfer electrons back into the Q pool and just pump protons. That just goes around in a little cycle, and no NADPH is produced, but it just pumps protons, and that can be used to synthesize ATP, and we don't have quite enough ATP. Okay, now this summarizes all that, so I've written all this out here to make it clear. The overall net reaction of both photosystems is 2 waters plus 2 oxidized NADP goes to 1 oxygen and 2 NADPH. That reaction, as written, has an energy change, delta G0, of plus 440 kilojoules per mole. This reaction is coupled with the transport of 12 protons, as I've mentioned, across the thylakoid membrane, and that synthesizes about 3 ATP. It's actually a little bit less than that because the ATP synthase in chloroplast has 14 C rotor subunits. Remember that there were 8 in the mitochondria. So it's kind of like a different drive shaft and a different rear axle, if you like, on a car. And this one has a lower gear so that it needs more protons to produce a given amount of ATP. But for this class, we'll say about 3 ATP. Now, here's the energy of light. This is a formula. The energy of light from the original equation is h nu, as you know. It can also be written as hc over lambda, where c is the speed of light, lambda is the wavelength of the light. And putting this in units that are useful to us, that's 119,710 divided by the wavelength of light in units of kilojoule per Einstein. What's an Einstein? That is a mole of photons, okay? Rather than a mole of molecules, it's a mole of photons. If you use red light, 680 nanometers, that corresponds to an energy of 176 kilojoules. If we multiply that by 8 for the 8 photons, that's 1408. That's more than enough energy to power the electron transfer reaction that we've shown here. Okay? So we've got plenty of energy in these 8 photons to carry this out. One thing I wanted to mention while I'm thinking about it before I go back here is that this photosystem 2 has a special pair of chlorophylls that absorb at 680 nanometers, so it's called P680. The one in the photosystem 1 has a special pair that absorbs at 700 nanometers, so it's called P700. And it is the special pair that allows this to absorb at longer wavelength light, lower energy, that allows these special pairs to trap that photon that's coming from all of these accessory pigments. Okay, so I think this would probably be a good time to take a couple minute break here, and then we'll come back. And what I'm going to do next is to look at the crystal structures of these proteins. In the last few years, these structures have been worked out, and they've given us some amazing information